Okay. Right. Whoops. Whoops. What's wrong, Donna? What? I've bad news for you. You're the only two girls in the class, so if I hear a girl's voice, I know who's talking to who.
But it's not my fault.
Oh, it's her fault? Okay.
She touched my friend.
Oh dear. She's a troublemaker, yeah? Alright, number 4. 2013 B4. You see that picture there? It's a slide. So there's a boy sitting at the top and then slides down all the way to B and then back up to C. Question 1. What is the maximum kinetic energy? Where will the maximum kinetic energy happen in this diagram? A, B, or C? B. Yeah, and in fact the kinetic energy at B will equal what? Potential energy at A, which is mgh, which is 50.6 times 9.81 times 20.5, which equals 10176 joules. Is that okay? Did you get that as well when you typed it in? Yep. What is the velocity of the boy at C? So, what you say is the energy at C equals the energy at A or at B. In fact, let's just go with A. So the energy at C is kinetic energy at C plus potential energy at C equals potential energy at A. Or, as you said, Tanish, kinetic energy at B is fine also. I feel like confusion has set in.
Yeah, I don't get the equation. Well, why is it kinetic energy at C and potential energy at C?
It's the total energy at C. He's traveling at C, so he has a kinetic and a potential. He's not at rest, or he's not at the ground. Is that okay?
Yeah.
What's that? That's what he's asking me right now. Can you explain it to him, please?
No, it's because the energy at A must be equivalent to energy at C.
Yep.
So the energy at A must be equivalent to kinetic energy at C plus the potential energy at C.
Because you have both forms.
There's no maximum or minimum. That's like
It's just in the middle.
that's both. There is kinetic and potential.
Yeah.
So the total of it must be equivalent to energy at A.
Yeah, which is only potential.
Yeah.
And we have that number already.
Because at A the kinetic is 0.
A half mv squared plus mgh equals 10176. So I get, and that height there is 5.6. So a half mv squared plus mgh equals 10176. 10176. I got 17.097 about. Yes, phi is 17.098. Yeah, we'll go with 17.1. 17.1 meters per second. Alright, now, whoops. No, that's the A part done. On to the B part. Okay. Who remembers what does geostationary orbit mean? So in this example here we have the satellite going around the Earth. Does anyone remember what geostationary, that's one word. Say again? Very good. T is 24 hours. I also called it, there's another name for it, there's geostationary, or does anyone remember the other name for it? Parking orbit, or stationary orbit, I guess. Geostationary or parking. Okay? Yes? It's a term. If you didn't remember it, there it is there. Okay. Part 2. What is the height of the satellite if the radius of the Earth is this? So I'll draw it here as best I can. There's the Earth, and we're given its radius is 6,378 kilometers. And then the satellite is up here, height h, and here's the satellite here. Okay, so that's the satellite. And they want the height. So we know that it's moving in a circle. So we could use our circular formulas. Yes? We also know that we can use Newton's law of gravity as well. If I want to use my circular formulas, I could go with T equals 2 pi over omega. So I can get the omega. Let's do that first. 2 pi over T, which is 24 times 3,600, very small, 7.272 times 10 to the minus 5 radians a second. Radians per second. Sorry, it's off the screen now. Okay. Right, that's okay. But what other formulas do we have? We have V, what else do we have? We have a formula for force, don't we? We have force equals m omega squared or. So let me just call this big one here or. Do we know the m? No, we don't. But we have a formula for F. What's the formula for F from Newton's second law? MA. So I get A equals omega squared or. Do I know the omega? Yes. Do I know the A? No. But now I have Newton's law. F equals G m over r squared. Newton's second law, what does this F equal? M A. Right, hang on, this is big M and this is small m. Yep.
I thought the D was for meters.
Of the Earth, not of the orbit. Right. Yes. Now the m's cancel here, so we end up with A equals gm over r squared. We can make these equal. So we get omega squared or equals gm over r squared. Oh wait, nobody told me they gave me the mass of the satellite. It says it's 185 kilograms. Do you see that? All right, forget. Right. Let's do this again. So we know the mass of the satellite is 185 kilograms. And we know the omega. Right, what other formulas do they have? Let's see if there's one here that's useful. Circle. F is... Well, yeah, I think I might need to use Newton. You mean the big F one?
Yeah.
Equals G m over r
Squared.
squared. So we could make these equal, but I'm reluctant to do that because the small m's cancel, which I know. So I don't really want to do that. I know the small m. Hang on. Teacher's getting tired. Just give me a moment. Say that again? Do we know the mass? Or we could know the mass of the Earth.
It's already there. Given.
The mass of the Earth is given. Ah, that's later. We can't really use that. Alright, we'll get the mass of the Earth. Okay, GMM over R squared, we make them equal, so we get M omega squared R equals GMM over R squared. This is actually Kepler's law here. The M's cancel, so we get, No, they don't cancel, yeah. R cubed omega squared equals GM. So M is omega squared or cubed over G. But we don't know this. We need to find it. But we don't know this. Huh?
We have to find out.
Yeah, but that's with the Earth.
I thought it was the muscle.
Well, you know what? I'm not going to make the same mistake I did yesterday. I'm trying to rush through this at the end of the class.
You can just actually find the
No.
mass of the Earth without using everyone's. Like
How would you go about finding the mass of the Earth then?
using.
What?
Yeah, it used the method.
It uses it.
Yeah.
Dirty cheaters.
It used it.
But it doesn't say it until part.
And it used the geo too. The 6167.
Oh, well, that's fine because that's a constant.
But this Earth also it used
You
the
can
Earth.
pick a random object already on the Earth's surface.
Yeah, but you're saying in the answer they use the mass of the Earth.
Yes.
But that's not given until part 4.
How is it supposed to be?
You can cheat.
If they did it, we can do it. So we'll go with that then. That's strange. So, note, students, listen. This question did not provide me with the mass of the Earth. However, later in the question it does provide me with the mass of the Earth. So I guess I'm allowed to use that. So we know small m is 185 and big M is 5.974 times 10 to the 24. Right. That's great now. So what did I've removed the formula. I had it here a moment ago. What did I just have a moment ago here for R cubed? It was R squared, R, yeah? GM. Now, I know this. I know the last one. So I can get this one here. R cubed equals GM over omega squared. 6.67 times 10 power minus 11 times 5.974 times 10 power 24 divided by omega 7.272 times 10 power minus 5 squared and then cube root. So here you get R is 422371334. But that's the radius orbit, and they want the height. So what do I need to do with this number? Minus 6378000 and I got 35860 kilometers. Is that right? That seems really big. What's the answer there, soon? Okay, yeah, so it's right there. Yeah. Okay, that is part 1, part 2, and now part 3. What is the velocity? So what's the formula for velocity? Omega.
Square arm. Omega r.
Yeah, well, actually, yeah, we're using omega equals v over r, so v equals omega r. So do we know the omega? Yes. Do we know the r? Yes. So we just multiply those numbers together. The omega is 7.272 times 10 to the power of minus 5. And what was the orbital radius? It was 422,37134. 3071 meters per second. Right. Last part is, what is the density? What's the formula for density? Mass over volume. What's the mass? 5.974 times 10 to the 24 all over volume. And who remembers the formula for volume? It's 4 over 3 pi r cubed. And the radius of the Earth is 6378000. So I'll just type that into the calculator. Let's see what we get. 5.974 times 10 to the power of 24 all over 4 over 3 by pi by 6378000 cubed. 5497 kilograms per meter cubed is what I got there. Last part, C. The satellite collides with some space debris of mass 80 kilograms. So this is just conservation of momentum. What you've got is your satellite. How big is my satellite? 185. And then there's some junk here in space. 80. How fast is my satellite going? What was its speed? Can you tell me what was its speed I had it a moment ago? 3071 meters per second. And then the speed here, well, we'll just say 0. Does it?
Same speed.
Well, yeah, it should really be the same speed if it's been in orbit, isn't it? Yeah, same speed, so it's not 0. It is also 3071 meters per second. So what formula do I use here if I want to know the speed of when they're combined together? Conservation of momentum. M1 U1 plus M2 U2 equals M1, well, the combined mass times its new speed. By the way, does the question say they're traveling in the same direction?
Yes.
No! No, it's traveling in an opposite direction. So what do I change here in my formula? That plus should be a minus. Alright, let's see what we get. 185 times 3071 minus 80 times 3071 divided by 185 plus 80, and I got x equals 1217 meters per second. Okay? Now, the next part of the question, the last part of the question is, after they crash, you can see the satellite is going slower, yes? So this means its orbit has decreased. And they would like to know what is the height now. So we can use, so let's write down our formulas. We have omega equals v over r. We have f equals g m over r squared. and we have F equals m omega squared or. Now, what do we know? We know the V. Yeah. We will assume, well, I don't know if we should assume that it's still geostationary.
Space-time?
No, when they combine together. Should we, what do you think? Should we assume it's still geostationary or not?
Just Alan and space-time?
Yes.
No, they won't be geostationary.
I don't think so. So what do we know? We know the V. We don't know the or. But we do know the masses, and we do know the G, but I don't know the or. Let's look at this one. I don't know the omega. Well, here, this can also be written as v squared over or, if I put this one in here. Alright, I know the m, I know the v, I don't know the or. Do I? No. Combine this with these two together. Let's see what happens. Gmm over or squared equals mv squared over or. This one cancels this. This one, this is great. V equals square root gm over or. That looks terribly familiar, like I've seen that before. Anyways, yes, it was something like that, wasn't it? Anyways, square root fraction. Huh? Oh yeah, sorry, I have to rearrange this. So if I square both sides, I get or equals gm over v squared. Okay. 6.67 times 10 to the power minus 11. What's the mass? 5.974 times 10 to the power 24 divided by, now what was my velocity please when they combined? 1217? And then don't forget that this is the orbital radius. We have to take away the radius of the Earth if we want it as a height above the Earth. So minus 6378000, and now I get 262658 kilometers if you want it like that, or whatever. 263 times 10, it doesn't matter, just leave it as kilometers. What's the answer there, soon, if you have it? Does it start with a 2.6? Yeah, okay, fine, yeah. Okay.